Hello, good morning to everybody, and welcome to this second session of this last day of ADMOS. And this session is the very multi-session. It's multiscale, multimodel, and multiphysics. We got 5 talks planned for this session, and then after that we're going to have plenty of time for the discussion. So I think we are all experts of using Zoom in this conference. Make sure that you use the chat to pose any questions. If you can direct the questions and tell me to which speaker this question is posed, that would be great. And then at the end of the 5 talks, we'll have time for this discussion live. So let's make a start. By the way, my name is Ruben Sevilla. For those who don't know me, I'm from Swansea University, and I'm going to be chairing this session, obviously. And the first talk is by Pearl Jung, and the title is A Space-Time Multiscale Method for Parabolic Problems with Space and Time-Dependent Coefficients. Please, you can play the video.
Hey, my name is Per Jung, and I'm from Chalmers University of Technology and the University of Gothenburg, and I will present our space-time multiscale method for parabolic problems, which is a joint work that I've done with Roland Meyer and Axel Målqvist, who both are from the same universities. Now we consider this parabolic equation, which is just this standard parabolic equation, and we have this boundary and initial value condition as well. But the important part here is that this diffusion coefficient, it has these rapid variations in both time and space. Now, equations that usually have these rapid variations in the coefficients, they are commonly referred to as multiscale equations, which they appear usually when you model like porous media or composite materials, etc. And the tricky part about these so-called multiscale equations is that if you try to solve them with, for example, like the finite element method, then the problem is that the corresponding finite element mesh has to be so refined that it can resolve all of these variations in the diffusion coefficient. Now, if the diffusion is very rapidly varying, the problem is that you have to have such a fine mesh that it's just not computationally feasible. So this is why you develop these sort of multiscale methods that are more suitable for these types of problems. Now, the main idea of our method, so first of all, it's based on another multiscale method known as the variational multiscale method. And the goal is to extend the framework of yet another method known as the localized orthogonal decomposition method. And by extending it, I mean extend it into the case when you have these space-time varying coefficients. So the main idea is that you have a solution space and you decompose it into a core space and a fine space, respectively. Now these spaces, they have their separate parts. So the fine space, which first of all is so fine that it can resolve all of the variations that I talked about. Now the fine space has the purpose of computing these so-called correctors. And the correctors, they contain information on how the diffusion vary on the fine scale. And then you take these correctors and you incorporate them into a problem on the core space. Now you can solve this space on the core space quite cheaply, but still have these good approximation properties since you now have the information on how A varies on the fine scale. And that's the main idea of the method. So the ideal method is defined by solving the weak form on this core, by considering cores and fine test functions respectively. And then you get these two equations. The fine one defines the correctors and the coarse one defines the main equation. And then we can derive the following theorem for the method. That is, without introducing too much notation, it states that if the source function is sufficient, has this sufficient regularity, then the error of the ideal method will converge linearly in the H1 norm. So like in both time and space. So you have this optimal order convergence. The only problem is that the ideal method is based on these global fine computations on the fine space. And this is very expensive, and it's exactly what we wanted to avoid to begin with. So without going into too much details, I will just state that you can localize the method so that you have this localized variant of it. So instead of computing it like on the global patch, you compute it on small localized patches. And then you have a computationally feasible method. So I'll just wrap up with this quick numerical example. So we have a unit square, and the diffusion is generated by just a bunch of random values with a frequency of 2 to the power minus 4 in both time and space. You have the fine time step and mesh size that is so fine that it can resolve the variations in the diffusion. And you let the coarse parameters, like this is the coarse time step and this is the coarse mesh size. You let them vary between different sizes, and then you plot the relative error between our method and the reference solution. And then you get this error plot. So the black line here states the linear order convergence, and the blue line is our method. And I should also state that it's the localized variant of the method. And we see here that it satisfies this optimal order convergence. Thank you.
Okay, brilliant. Thank you very much for this talk. We're going to move to the second one, which is going to be delivered by Roland Maya. And the title is Multiscale Scattering in Nonlinear Kerr type media.
Hello, my name is Roland Maya from Chalmers and the University of Gothenburg, and I will talk about multiscale scattering in nonlinear Kerr type media, which is a joint work with Barbara Verfurth from Karlsruhe Institute of Technology. The motivation of this work is the so-called Kerr effect, which occurs when a high-intensity light wave traverses certain media, and it induces nonlinear scattering behavior due to a change of the refractive index. In a time harmonic regime, this problem can be modeled by a nonlinear Helmholtz equation with a wave number k and certain material coefficients a, n, and epsilon, where gamma here is the boundary of the domain D. Here we specifically consider highly oscillatory media, for instance, so-called metamaterials, where the coefficients a, n, and epsilon can possibly vary on very fine scales. Yeah, when discretizing this problem, one is mainly faced with three important aspects. First, due to the nonlinearity of this problem here, we require certain linearization strategies. Then, in order to handle the multiscale behavior, due to the fine oscillations in the coefficients, we need very fine resolution of the underlying mesh, which can be very expensive. An alternative here is to use so-called numerical homogenization or multiscale techniques, which already work on very coarse scales and take into account in a sophisticated manner the fine oscillations of the coefficient. And then the third important point is to reliably combine the linearization and multiscale techniques, and there also some sort of adaptivity will come into play. Due to time constraints, I will not have the time to talk about these 3 points separately, but I will instead directly move to the final adaptive multiscale method and sketch its construction. First, we require a linearized form, blin, where this nonlinear term is replaced by some auxiliary function phi. Then we can use this in order to construct an adaptive iterative strategy with the multiscale method LOD. What we do here is we take the previous iterate and plug it in as our function phi, and then compute the new iterate based on this linearized problem here, which is posed in this adapted finite element space VH, where this VH space is corrected by this correction operator C. And this correction operator is constructed based on this multiscale technique LOD introduced by Morquist and Petersheim 2014. And here we update this correction in each step, partially based on some given error estimator and some given tolerance. Finally, one can then show the following error estimate. Namely, we can show that in the nth iteration, our solution is close to the actual solution in this energy norm up to 3 main terms. The first one here is the coarse mesh size, which does not necessarily need to resolve the fine oscillations. then this tolerance that we have for the update of the corrections here, and then a third term, gamma to the m, which ensures that we get improvement with a number of iterations. All right, before I conclude, I'd like to show you a small experiment on the unit square, where we have an active nonlinearity in this lower right corner of our domain. We have some given wave number and coefficients that vary between certain bounds on this oscillation scale eta. Also, we have on the right-hand side a regularized point source f that starts in the middle of the domain. All right, for this, we have the following error plots. Here in the left plot, we see the errors in blue of the multiscale method after 20 iterations. And here we see a nice linear convergence rate in H, independently of the oscillation scale of the coefficients. And then we also have in red an iterative finite element method, which stagnates in the beginning or shows a reduced convergence rate and then only indicates a linear convergence rate once the oscillations are resolved. For completeness, we have here in the right plot also the behavior for some fixed mesh size H within number of iterations. And here we see a fast stagnation for the finite element approach, whereas the multiscale method shows nice improvement within the first few iteration steps until it reaches a point where the mesh size error dominates. Okay, with that, I'm already at the end of my presentation, and I'd like to thank you very much for your attention. And if you're interested in more details about this, feel free to have a look at this paper here, which is also linked on my webpage, or just contact me directly by email. Thank you.
Thank you very much, Roland. Very good. Questions are already coming up on the chat, so please make sure that you write your questions if you have one, and thank you for those that are already contributing. Next, we move to the third talk, which is going to be delivered by Modesar's Kerr, and the title is Computational Homogenization of Unsteady Incompressible Flows with Obstacles.
Welcome everyone to this video, where we talk about computational homogenization applied to fluid mechanics. So what I want to do is to consider and solve a flow problem in a domain where I have very small obstacles. So the size of the obstacle is very small compared to the size of the domain. For this problem, I can solve it using the Navier-Stokes equations with obstacles. And the problem is that I cannot mesh at the same time the domain and the obstacles. So I want to be able to separate the scales by using a theory known as homogenization theory. And this theory is well known and used for the simplified problem where I'm not considering the advection. In this case, I fall back to the Stokes problem with obstacles, and it is well known that we can homogenize this as the Darcy equations. Recently, it was shown that we can also consider the advection term and still use homogenization. And more recently, it was shown that we can consider all the terms, but in these works, the authors did not actually show a single simulation where we have at the same time a solve at the coarse scale and also at the fine scale, and we have a two-way coupling between the two. So this is what I want to do. I want to do something like Fe square. So I want to have a finite element mesh at the coarse scale. And at each point of this finite element mesh, I want to attach a fine scale domain, which I will call RVE, and for which I will also have a finite element discretization and solve. So here is the algorithm I'm going to use. So I'm going to have for each time increment a nonlinear problem to solve at the coarse scale. And to have the contributions from this coarse scale problem, I will have to solve RVE problems. So for each RVE, I will have to solve a nonlinear problem, a different nonlinear problem, for which the boundary conditions are going to be given by the coarse scale velocity and velocity gradient at some point of the coarse scale domain. And by solving the RVE problem, I will get the coarse scale force and stress to get the contributions for the coarse scale problem. And when I will converge on this Newton scheme at the coarse scale, I will have the solution at the same time for the coarse scale problem and also for all the fine scale problems. So there are two issues with this algorithm. The first one is the computational costs. So I will solve it using parallel computing and also an efficient memory management. And the second issue is that the RV problems are very hard to solve. And for this, I'm using a robust numerical scheme. So here is a first example of result. So what I did, I considered a plate with a hole, a plate of size 1 by 1. The Reynolds number is 5, and the velocity is in the horizontal direction. So this is the core scale. And the fine scale looks like the core scale, but it's actually smaller. And at each point of the core scale domain, you can see that you have a fine scale problem to solve. And there will be 2,500 fine scale problems to solve. And you can see that even with this coarse mesh that I'm using here, I already have 5 million fine scale degrees of freedom and 6 million fine scale integration points. Here is the result that I get. So on the left, you have the result at the core scale, which is an animation with respect to time. And on the right, you have the fine scale solution only for 3 points. So remember that I could show you 2,500 points. So you can see that the boundary conditions for the fine scale problems are really coming from the core scale. So there is really a coupling between the two. Something different is happening at the fine scale depending on where you are located at the core scale. The computation time is already quite big. So you can see it's 42 hours on 24 CPUs. And even though the number of Newton increments was quite reasonable, and I'm only in 2 dimensions. So now I'm interested in a few questions that I could investigate with this scheme. So the first one is, what would be the influence of RVE size? So here I use actually an RVE size, which is the same as the size of the coarse mesh. So what would be the point of using a larger RVE or a smaller RVE? And the second question is, would this scheme still work for larger Reynolds number and when we get closer to turbulence? And the last question is, what can this scheme also be used for more complex physics, for instance, non-Newtonian flows or multi-phase flows? So for the first question, I actually looked at this question by using a different domain size. So I used a domain larger than before. And you can see in the blue curve here that I get a different result. And what happens is actually when I have a larger RVE, the solutions get kind of diffused. So this scheme can also work, although I have not to investigate the physical meaning of this parameter. Thank you for following this presentation, and I will be happy to debate this scheme with you during the discussion session.
Okay, very good. Thank you for this presentation. Let me encourage all the participants to write questions in the chat. There are a few already. Let's move to the fourth talk, which is going to be delivered by Vin Tu. And the title is Numerical Model Reduction of the Electrochemically Coupled Multiscale Transport of Electroactive Species.
Hello, my name is Vin Tu, and I'm a PhD student from Chalmers. The title of my work is on the electrochemically coupled multiscale transport of lithium ions in structural battery electrolytes. Here in this figure we have a structural battery, which is a multifunctional material. It is basically a carbon fiber composite which is able to act as a battery because the carbon fibers are working as the electrodes. So in essence, we have a structural battery which is able to carry mechanical loads and at the same time store and deliver electrical energy. In my project, I'm going to focus on the electrolyte of this system. More specifically, we're looking at the lithium ion transport in the SBE, that is the structural battery electrolyte. You can see an image of it down here, and it consists of a solid phase and a liquid phase inside of the microstructure, and our goal is to use a two-scale modeling approach where we introduce a RVE that captures all these fine features. And then the goal is of course to jump back and forth between the battery on the macro scale and the RVE on the micro scale. But doing such a Fe² simulation is quite expensive, so we would like to exploit numerical model reduction to make it cheaper and more viable. And in this case, we'll be introducing a surrogate model which will replace the RVE simulations. And finally, we would like to be able to simulate the battery on the macro scale. Here we have our multiphysics problem and the governing equations. On the first row, we have the Ampere's law reformulated as a balance law. It lives only in the liquids domain because that's where we have our ions. And the same goes for the second equation. We have the diffusion equation that only lives in the liquid domain because that's where the ions exist. And in our system, the ions are not only affected by chemical diffusion, but also by electric migration. On the third row, we have Ampere's law again, but this time in the solid because the electric field is penetrating each and every medium. And then we have a bunch of other constitutive relations. Here we have a numerical example of a 2D RVE. We're applying a ramp on the macroscopic gradient in the chemical potential. We're basically telling the lithium ions to move along in the gradient directions. And here you can see the electric potential and the chemical potential, their distribution after a very long time. The next step is to start extracting snapshots for the numerical model reduction, that is for our surrogate model. We're extracting snapshots of different physics from different time steps. And these snapshots will serve as the training data for our surrogate model. So the more snapshots, the more unique snapshots that we can provide from different loading cases, the better the surrogate model will perform. And then we can use all of these snapshots that we have gathered to compute these modes that are computed via POD, that is proper orthogonal decomposition. We can insert these modes into our weak forms, and then out of it we can get this type of equation system. In this case, it's a first order ODE equation system. This is our surrogate model. And of course, we can simplify this surrogate model even more by putting it into the spectral format. That is, we're decoupling the equation system. And it turns out that when you do that, our surrogate model in the spectral format becomes analogous with the Maxwell-Zener rheology model. Now that we have our surrogate model, we can finally use it in an F² sense. So instead of jumping back and forth between the macro scale and the RVE, we're now jumping back and forth between the macro scale and then directly into our surrogate model, which is a much more cheaper procedure. Here we're putting our NMR model to the test. We are applying a macroscopic gradient in the chemical potential. We can see the blue curve, which is the reference. And then all of the rest of the curves are NMR response. And we see that the more modes that we're using in our NMR model, the better the approximation becomes. Ideally, we would like to try out more and different loading cases, but that's for future work. So all of this is still pretty much work in progress. So hopefully next time I will be able to show more. So that's it for me. Thank you very much for your attention.
Okay, thank you very much. Another very good talk. So let's move to the last one. Excuse me. Let's move to the last talk, which is going to be delivered by Christopher Carlson. And the title is on the use of flux boundary conditioning in the finite element square procedures with seamless scale bridging. So please keep writing your questions also in the chat.
Hello everyone and welcome to my talk. My name is Christopher Carlson and I'm from Chalmers University of Technology. And this is work I've done together with Fredrik Larsson and Kenneth Runesson. So first I want to say what problem we want to solve. We want to solve some PDE on a domain which includes micro-heterogeneities. So if we zoom in, we can see we have a lot of heterogeneities here and it will be computationally expensive to solve this in a fully resolved fashion. So we want to use some sort of homogenization strategy. Now, one strategy we could use is called model-based homogenization, where we assume that we have full-scale separation. And we can use the variational multiscale method to split the field here into two parts, one macroscopic and one fluctuation part, and we get one equation for each of them solved. And then we have to satisfy the Hill-Mandel condition, and different choice of boundary conditions can give different bounds and affect their properties. And typically, the Dirichlet boundary condition gives an upper bound, and the Neumann boundary condition gives a lower bound. So another way is to use what we call discretization-based homogenization, and then we assume the domain is divided into a set of macro elements, and we use adaptive mesh refinements on these macro elements to drive it. Depending on the size of the macro elements, we're in different regions. So if the sizes of them is much smaller than the subscale, we have the fully resolved case, we have no scale separation. If the size is much bigger than the subscale, then we have full scale separation. And in this intermediate region, we solve a set of what we call QE problems. And the ability to transition between these scale separations is what we call CIMNE scale bridging. So let's look at the QE problem. Here we assume that each macro element has a set of micro elements inside it. An integral over this macro element is approximately a sum over some of these micro elements, and the ones we pick are what we call quadrature volume elements. And we split the solution here, the field, into a macroscopic part and a fluctuation part. And the macroscopic part now comes from interpolation of the macroscopic field based on the nodal values. And then we need to find a homogenization operator so that this fluctuation actually is a fluctuation. And if we apply it to the solution, we get back the macroscopic solution. And if we apply it to the fluctuation, we get 0. And this homogenization operator will give an extra constraint here. And I'll show the form here. It involves an inverse of a mass matrix here, which is the shape functions of the macroscopic field. So we're going to apply this to the heat equation. And here's the primal format, which is completely the standard way of writing the heat equation. We get a macro scale problem, which involves a sum over these QEs then. And we get a restricted QE problems where we have that the fluctuation field is 0 on the boundary. This we can enforce via Dirichlet boundary condition. So we have a standard weak form here of the heat equation, but we also have these extra constraints from the homogenization operator. And then we have the heat equation again, but in what we call the dual format. And then we have that this constitutive equation is its own separate equation here. So we have two primary fields. We have the temperature and we have the heat flux. And then we get a macroscale problem involving two equations, and we have a QE problem here, a restricted version, where we have that the normal flux here is 0 on the boundary, and we enforce that here. It will become a Neumann boundary condition. So here we have two equations here on the QE problems, where we have these constraints as well. So we have in total 4 equations, and 2 of them are coming from the extra constraints from the homogenization operators. When I look at some numerical results, we have some domain here where we have a bunch of tiles on it, and we have such that we can fit 32 tiles, and each tile has 2 particles in it. We let heat come in here on this boundary, and we set the temperature to be 0 here, and the red parts, it's fully isolated. And we have different material properties inside the particles here and inside the surrounding matrix element. So if you want to look at some numerical result, we can vary the number of macroscopic elements and look at the solution for the dual and the primal formulation. And here we use all the microelements as QE, which is what we call full integration. And we can see that the solution is approximately the same between the dual and primal. To get a bit more quantitative, we can look at some effective property here where we integrate the temperature along the line where we let the heat come in. And we can see that the dual case here is above the overkill solution, and the primal case is under here for the temperature. Thank you.
Okay, thank you very much to all the presenters. Please make sure that you write your questions in the chat if you have questions, especially for the last one. And we got some questions already there, so I'm gonna start in order following the chat. The first question is for Per Jung. And the question is from Frederic Legol and says, can you please detail which PDE that LOD corrector solve? Is it the parabolic PDE of interest? And if so, until which time? Or is the elliptic problem?
Okay, can you hear me?
Yes.
All right. So I guess the short answer is that it's the parabolic PDE that it solves, but it's quite a complex answer in reality. So basically, we have this tensor product space in space-time. So we have this space, like finite element space for the spatial domain, and then you have this a finite element space for the temporal domain as well, and then you have this tensor product space. Then you take the weak formulation, and so it's based on the variational multiscale method. So you have this decomposition of a fine and a coarse solution. So you plug this into the weak formulation and you consider fine and coarse test function respectively, and then you get this equation on the coarse scale and this equation on the fine scale as well. So what we do at this point is that we take the fine scale equation and decompose it so that we just consider these space-time basis functions. So we have these basically pyramids in space-time because it's the tensor product of the hat function in space and hat function in time. So for each such basis function, you compute this parabolic problem on the fine scale. And then the question was, how far do we compute it? And that's where this localization part comes in, because at first you have this ideal method, and then you compute it on the entire temporal domain. But this is, I mean, you have this fine grid on the temporal domain, so it's quite computationally heavy. But what we realize is that these temporal basis functions, they decay very rapidly. So we only have to compute them for, say, 2-3 coarse time steps before they have basically vanished. So that's one part of this whole localization procedure that is introduced. So I guess that's the more longer complex answer. And the short answer is yes, it's the parabolic PD that we consider.
Perfect. Thank you very much. Second question is also for you, is from Frederick Larsson and says, can you elaborate on the multiscale behavior in space versus time for the parabolic problem? In the example you chose t equals to h, are there other interesting alternatives?
Yeah, so the variations in space and the variations in time, they can be completely independent in general. The only requirement is that the fine grid in space can resolve all of the spatial variations, while the fine grid in time can resolve all the temporal variations. So you can have very fine variations in time and not so fine variations in space. But then the requirement is that the temporal grid is very fine and can resolve the temporal variations, while the spatial mesh that can be quite coarse, and just as long as it resolves these small variations, then so they can be completely independent. So in my numerical experiment, I only used like the coarse parameters were equal, and that's because the error estimate that we have proven is an error estimate result based on these coarse parameters. So they are supposed to decay, like they are supposed to converge linearly in both the coarse and time and space. So that's why I use it. I just set them to equal and show that they decay linearly. But when it comes to these variations, it's the fine mesh and fine time that is relevant. And they can be chosen arbitrarily just as long as they can resolve the variations. Is that an answer to the question?
Yes, Frederick is confirming in the chat, so thank you, Per.
All right, great.
Brilliant. The next question, let's move on to Roland. The question is also posed by Frederick Lecole, and the question is, do you recompute the LOD correctors at each iteration M, at least in the subdomain where you know you have some non-linearity?
Yeah, can you hear me?
Yes, and we can see your screen.
Okay, perfect. So this is a very good question because this is the essential part of this method. So since in each of the steps we have a new linearized form, this also would mean that at least theoretically one should recompute everything in every step. But this is not what we do. Instead, at each step, we look at our new function phi that we want to put in here and compare it to the previous one. And if the difference there is relatively small in an L infinity sense, and then we also have another term in this kind of error estimator that we have for this, then we can decide locally if we want to update the correction or not. So the correction is computed based on this linearized form, and everything is localized. So for each course element, we compute a part of the correction. And for all of these parts, we can separately decide whether we want to update it or not. And everything like this can be done in parallel because there's no relations between the different localized parts. So in the end, for the experiment that we had down here, for the blue curve, we updated 5 to 10% of the correctors, and it decreased. So in the beginning, of course, for the first step, we compute all of the corrections, and then the next step, it rapidly goes down already, and we computed like 10% only, and then it goes down to 5. So it decreases quite rapidly, and we don't have to update everything in every step.
Very good.
Does that answer the question?
I think it does. Let's keep an eye on the chat, but I think it does. Thank you very much, Roland. The next question in the chat is for Modesar. The question is by Yanis Amouche and says, yes, Frederick confirms, Roland, that your answer was perfect. So thank you. The question for Modesar: what do you think about using machine learning to get the constitutive relationship for the RVE to bypass the finite element problem at this scale and solve for the micro finite element problem?
Yes, that's a good suggestion. So it's something that is, I would say, nearly systematically done for FE square now. I'm actually working on this topic, although I'm not sure it would work well for this problem because there is a significant path dependence. So it's kind of like in plasticity. And I think machine learning for the moment has some issues in dealing with this kind of problems.
Okay, thank you. Don't go away because you got more questions in the chat, a couple more for you. The next one is from Frederick Larsson and says, when you change the size of the RVE, does that correspond to change in the physics, so obstacle size and spacing, or do you sample multiple obstacles in one RVE?
It's a good question. So for what I've shown in the presentation, it's actually, like you said, changing the physics. So the obstacle size, the RVE size, and spacing changes. Now, in my experience of first order homogenization in solid mechanics, in statics, you have only dependence on the displacement gradient. And normally there is no size effect. So that's one of the, I would say, drawbacks of first order homogenization is if you take a big domain or small domain, as long as the volume fraction is the same, you have no difference. And in this case, I have a difference. I don't know if it's due to the fact that it's a flow problem or if it's due to the fact that I have a velocity term and not only the velocity gradient.
Okay, thank you. More questions for you, actually. Right, Yanis wants to continue the discussion. I might be wrong, but there has been a few good papers about machine learning for path-dependent problems, such as fracture or elastoplasticity. So I presume that there is a discussion going on there that you can continue with Yanis. The next question is from Alexei Losinski, and is two questions actually. The first one is, what are the boundary conditions on the RVE?
So it's I'm applying the velocity and the velocity gradient from the core scale. It's applied through Lagrange multipliers. So it's applied, so for instance, the velocity is applied like a distributed volume force. Mm-hmm. And the velocity gradient as like, it's not really a force, but a distributed stress. It's not really applied on the boundaries.
Mm-hmm. The second question from Alexei is actually a question that I also had for you, so that's great. It says, have you evaluated the error of your multiscale method with respect to the reference solution? So I was thinking exactly the same. Have you performed a DNS simulation and compare your multiscale to it?
Yes, that's a very good suggestion. So this is something I haven't done yet. Yeah, it's an expensive simulation, so I will have to set it up and run it.
Certainly, yeah. Thank you very much, Modesar. So let's move on. We got now few questions for Vin2. The first one is also coming from Janice and says, do you have an idea of how much you can reduce the computational cost using a finite element plus a surrogate compared to using a purely finite element squared approach?
Yeah, so that's not something that we have done yet or tried yet. So of course, hopefully we'll do it in the future, but it's very clear that we'll receive some kind of time saving by using this approach that we're using. So we're essentially like comparing the time to solve the full RVE problem with a fine mesh of its own versus solving just a first order equation system. So, and in practice, you would have one RV problem per Gauss point. So the larger problem you have, the more time saving you would be able to receive. So in essence, or in theory, you would have infinite time saving, basically.
Okay, thank you. More questions for you, Vin. The next one is from Pedro Diaz. It says, in many applications, I don't know if this is the case here, the problem for the RVE may depend on some local state variables. Do you think that it would be worthy to use a reducer of the model like PGD, providing an explicit parametric dependence, taking the state variables as parameters?
All right, so we're using POD right now. I'm not too familiar with PGD, but hopefully it's very closely related. And in my case, we have like linear transient coupled problems. So we don't have any special local state variables, I guess. So unfortunately, I don't really have an experience regarding this. So I can't really make a good comment regarding this.
Right. Had a similar question actually. If you thought of using, apart from the POD, if you thought of using PGD or machine learning in this case, but I think that's something to consider maybe in the future.
Yeah.
The next question is from Kiran Sagar. Again, it's for you, Vin. It says, very interesting talk. Do you think it is possible to replace the POD model with the viscoelastic model as a surrogate for RVE?
It might be possible, but I'm not too sure about this. I think it might be difficult to kind of like calibrate or tune the parameters for the viscoelastic model. In our case, we simply get all of that by performing our training phase, so to speak, within the POD. So as soon as we collect good enough snapshots, then we'll get all of that for free, so to speak.
Okay, brilliant. Thank you.
Yeah.
Going down, I can see a question from Frederick Ekre. Is to Christopher. The question is, do I understand correctly that different macroscopic elements in the same simulation use different procedures, like QVE, finite element squared? If so, how do you determine which method to use for a given element?
Yes, thanks for the question. I will share my screen quickly.
Yeah, perfect.
So indeed, the whole point of this system is to use a different type of solving based on the size of these macro elements. So in this, the numerical examples I showed, for example, these, I only showed the QV approach. But when we want to solve the full thing in a later stage, we would indeed choose between these different methods depending on the size of the macro elements. And what determines which one you use is the relation between the size of the macro elements and the size of the underlying subscale or the underlying fluctuations. So if we look at the numerical example, we can see that the fluctuations are related to the size of these particles, for example. So it's the relation between the size of the macro elements and the size of the particles in this case that would determine which of these methods we would use.
Very good. Thank you, Christopher. Please write any more questions if you may have them. Otherwise, I'm going to ask one to some of the presenters. For example, if I'll go in order to pair to start. The technique that you presented, is for transient diffusion problem. I mean, the question is, can this be extended to other problems like convection diffusion?
I'm not sure yet. This is the first thing we've experimented on, but some further research is to try to adapt it to other equations and see.
Mm-hmm. Okay. Can I ask Roland a couple of questions maybe? The first one is out of curiosity because I know a bit about the problem, but not as much. So the example that you selected, the wave number, you put the number, I think it was 17 or 20, something like that in the example, but is that large enough in order to make sure that the nonlinearity is a dominating effect in the problem? I guess so, but out of curiosity.
Yes, it's large enough. So you can actually see how the nonlinearity affects it. And if you have a look at how the linear problem looks like and how the nonlinear problem looks like, you see quite a huge difference actually. In
the bottom right, all the differences in the bottom right solution, is that correct?
Yes, yes.
Okay. And the other question, again, is out of curiosity. I noticed that you're using a scalar diffusion in your presentation. Is the extension to non-scalar diffusion easy, or there are some complications hidden there?
No, it can actually be done. So it's just a thing with implementation, to be honest. So, okay. But there's nothing in the theory that would prevent that from not working.
Okay. I think we got actually in the chat a question for you right now. Okay. It's from Manisha Chetri and says, a very silly question. There are no silly questions, but I'm just a bit curious to know what led to a stagnancy in the conversions of the finite element solution in your last slide, as I see that you reduced the element size as well.
So the point is that is basically what happens when these kind of multiscale equations have this mismatch between a fine scale on which something oscillates and a coarser scale on which something is to be approximated. And that's exactly the case here. So the problem is, let me just maybe share this once again, so we can have a look at this. All right, I guess you can see that. Mm-hmm. So I think we're talking about this curve here. So here we reduce the mesh size, but it doesn't really improve that much. And that's exactly the multiscale behavior. So the oscillations that we have in the coefficients, they're like on this scale here. And if this is not resolved by the finite element method, then the finite element method just produces a wrong result kind of. So the problem is that this is exactly why these multiscale methods are considered, because in this regime where something on a fine scale is not resolved, we still want to get something that converges linearly, but we don't get that with the standard finite element method. And there's a lot of example, for instance, in the elliptic case where this can be seen, that if you just naively take your finite element approximation, then you would just converge to the wrong solution if you're not in the regime where you resolve fine oscillations. So that's exactly the reason why this looks like this.
Okay.
I hope that answers the question.
Thank you, Roland. Okay, let me check the chat. Yeah, Manisha is confirming that you answered, so no new questions. So let me ask one question to Modesar. I mean, it's very interesting, the technique, and the results are very promising. I'm just interested on future extensions. So what about extensions to transient flows to start? Is it something feasible, do you think?
So what I showed actually is it's a transient flow, although yes, it reaches a steady state after some iterations.
But you solve it in a pseudo-transient manner.
Yes.
So exactly. You solve it with a time stepping until you reach a steady state. So in that sense, you believe that transient is not going to make any difference, correct?
Transient will not make a difference, but for instance, high Reynolds numbers, I'm not sure. I'm not sure it will work. I think it's because the theory is not complete. For instance, there is no stabilization, and there is no, I would say, there is nothing in the theory that handles the fact that you have different scales of turbulence, for instance, in the fine scale. So that there is nothing to deal with that. And also the numerically solving these equations for a high Reynolds number would be very difficult.
Okay. And the extension to other type of flows, I'm thinking on compressible flows, because I believe you are tackling the incompressible case, correct?
Yes.
Adding the extra equation to treat the compressible flows, is it something that can be done also?
Yes, I haven't really looked at it, but I don't think that would be very difficult. What I'm interested in actually now is multi-phase flows, which is a little tricky because you have to handle that you have two phases at the fine scale and the coarse scale.
Yeah, yeah. Okay, thank you. I cannot see any more questions in the chat, so I'm gonna keep satisfying my curiosity here. Vin2, please, can I ask you about the sampling?
Yeah, right, yeah.
You're doing sampling for constructing your surrogate model with the POD.
Yeah, exactly.
How do you do that? I always find this is interesting to know from people that are actually implementing these methods. How do you sample? How do you make sure that the sampling is rich enough? And is it something that you do automatically, or how you do it?
Okay, right now it is a bit manual, to be honest. So it's quite a lot of error and trial, unfortunately. Hopefully we'll be able to automate it in some way in the future at least. But right now we are basically solving for the full RVE problem, you know, the reference solution that contains the physics that we want to solve for. And then we are basically looking for where we have the most transient effects, essentially. So the loading cases that we're applying to our RVE problem is something like a Heaviside step function. So we try to do it to activate as many frequencies as possible, so to speak. So analogous to some kind of impact testing. And then, yeah, we basically sample or take snapshots from all different physics from different time steps.
Okay, thank you very much. No new questions in the chat, so I'm going to move to Christopher, if I may ask you one question. In the last slide, I was curious about these things about the bounds, right? You got that the primal formulation seems to provide a better bound than the dual, in the sense that it's closer. Is that something that it is correct?
So what you're meaning is why the distance here is further than the distance here? Or?
Yeah, is it a matter of this particular problem and is not important, or is something that is actually something you can prove that the bound is a bit better for the primal compared to the dual?
I don't think it should be a general thing. I'm not sure why it happens right here. I mean, what we should do is, you see both of these curves are quite flat right now, and in general we want to like capture a more larger region of this. So for future simulations, we will want to basically have a bigger span here, so we could see further to the left and further to the right on these curves and see how things converge a bit better, and then maybe we could more accurately answer that.
Okay, and you're using a dual formulation. It's like a mixed method, correct? Where you approximate the solution and its gradient as independent variables. Am I right?
Yes, exactly. So if I show the dual formulation here, we have both the Q here, the heat flux, and the temperature are sort of independent variables. They have their own equation, and they're both living in the nodes of the element. So.
And I mean, have you considered what special? Let me ask you first, maybe what special discretization you're using here? What method?
We're using Taylor-Hood elements basically, so quadratic interpolation for the heat flux and linear for the displacement. So they have the, otherwise you have some instabilities, the insup conditions and so on.
And have you considered to use there are some methods that when you solve the mixed problem like you're doing, the fact that you're approximating the solution U and the gradient Q, which are basically related, but you solve them as independent variables, there are some methods that allow you to basically provide some error indicator using the information that the Q is actually related to the gradient of U, despite you solve it as an independent variable. Have you considered any of those?
We have not considered that, but that sounds interesting to look into. That would mean you could more accurately solve the problem then, or would it serve as an error estimation for like adaptivity, or?
Yeah, I mean, we've used it for it's not an error estimator, to be honest. It's an indicator only, but at least it can be used to drive adaptivity. So
yeah, because when we're going to solve the whole thing later, we want to use adaptivity for sure. So we need to find some good type of estimating there or there. So there it could be very useful.
Oh yeah, it might be of interest. I don't know. I was thinking about that. Okay, thank you very much. Final check on the chat. I cannot see any more questions from anybody. So I think it's 7 minutes to 11. Let me share my screen 1 second again. Okay. So I think I'm going to close the session in here because I cannot see anything else coming up on the chat. So you're going to have extra 6 minutes to have your coffee break. So the next session is starting at 11:15, and it's a session on industrial and engineering applications. So thank you to all the speakers, very interesting talks, all of them. And thank you to all the participants posing questions in the chat for contributing to the live sessions. Hope that you enjoy the rest of the conference. Thank you all.